Alright everyone, in this video I'm going to derive kinematic equation number 3. I'm going to show how we can get this equation. I'm not going to use graphs for this one, I'm actually just going to use the first two kinematic equations. And then I'm going to give you give you some insight as to why we have 3 kinematic equations and not just one. Because all 3 depict uniformly accelerated motion. Okay? Notice if you look here, I've left subscripts off. I've left the subscripts off of the velocities and the accelerations, and you're free to do that as long as you know exactly which direction you're dealing with. At this point, we're only dealing with motion in the horizontal or x direction. And so I'm going to leave off the subscripts, just knowing in my head that I'm dealing with horizontal motion. And the point for doing that is because the algebra here is going to get pretty heavy, and the less symbols we have, the easier it'll be to see what's going on. So to start this process, I'm going to take both of these equations and then kind of rearrange them a little bit, as we've had some practice doing. So kinematic equation number 1, I'm going to subtract the initial velocity from both sides. So it cancels there. And then I end up with final velocity minus initial velocity equals the acceleration times time. Note we have final minus initial something, and so we can always write that as delta, that something. In this case it's velocity, so our change in velocity is going to equal the acceleration times the time. And for reasons you'll see in a second, I'm going to go ahead and divide both sides by the acceleration. So now I have this equation solved for the time. And so that time value, then I have an expression for it. It's our change in velocity divided by the acceleration. I'm going to go ahead and put a pin in that and come back to it in just a second. I'm going to do a similar thing here with kinematic equation number 2. I'm going to subtract my initial position from both sides. And then on the left side, notice I have x minus x naught, or final minus initial position, equals, bring everything else down, initial velocity times time plus 1/2 the acceleration times the time squared. And just like I did over here, I have delta v representing v minus v naught, and I can do the same thing here instead of x minus x naught. Turn off the alarm. Sorry about that. So instead of writing x minus x naught, I will have delta x equals the initial velocity times time plus 1/2 times the acceleration times the time squared. So the reason that we solve this for time is so that I can actually take this expression here and substitute it anywhere I see time on the other side. So I'm going to take that expression and substitute it in both places where I see time t. When I do that, I get that delta x is going to be equal to the initial velocity times delta v over a. As I just substituted in for t, plus 1/2 times the acceleration times delta v over a squared. So I got to square that time. And so since time is delta v over a, time squared is delta v over a squared. Now you should know at this point your properties of radicals, or your properties of exponents. If you square an expression that has things in the numerator and denominator, then both the numerator and the denominator get squared. So I'm going to have to do that in the next step. I'm also going to expand my delta v's out back into v minus v naught for reasons that you'll see towards the end. So when I do that, I get delta x equals initial velocity v times final velocity minus initial velocity over the acceleration. Again, this is just a representation of the time, plus 1/2 times the acceleration. And then this delta v here, v minus v naught, must be squared. And so must the acceleration. Okay. I make liberal use of parentheses and brackets whenever I'm doing my multiplication. The dots get away from the x's, obviously you've gotten away from for a long time now. Parentheses I feel like are the neatest, cleanest way to do multiplication. Whenever you have multiple terms in here, when you have like a binomial like we have here, it helps avoid making mistakes. I can simplify this just a little bit right now. That acceleration cancels one of the accelerations in the denominator. I got one numerator acceleration, 2 denominator accelerations, and so the numerator one cancels with one of the denominator ones. And now rewriting, I have delta x. Now this v naught, you should be able to see, is in the numerator. If it's hard to see that, then just put it over the ninja one, the invisible one. You can put any number with no denominator over 1, make it a fraction. And when I do that, I note that that v naught must actually distribute over both of those terms in the numerator, with the acceleration just left by itself in the denominator. So when I do that, this term becomes the initial velocity times the final velocity minus the initial velocity squared. Right? V naught times v is v naught v. V naught times negative v naught is negative v naught squared. And again, that's over the acceleration a. And then I'm going to plus. Now notice this 2 is in the denominator, and so is this acceleration. So I can just rewrite this with a little more concisely with 2a in the denominator. But in the numerator, I got v minus v naught quantity squared. Now that's a binomial that I got to square. You should know this at this point. You got to FOIL that. If you got a binomial and you're going to square it, you got to FOIL it. If you can't go directly from this squared to v squared minus 2 v naught v plus v naught squared, then go ahead and work that out, rewrite it as v minus v naught times v minus v naught, both in the bubbles, in the parentheses, and then FOIL them out, and this will be the result. These aren't quite like terms though. I need to combine those in order to get kinematic equation number 3. They're not quite like terms. So what do I need to do? Well, I have a 2a here, I have an a here, so the least common denominator is 2a. And so to get the left term to have 2a in the denominator, I just multiply the denominator by 2. But what I do to the denominator, I must do to the numerator, because essentially I'm multiplying it by 2 over 2, so I'm multiplying by 1. So I'm not actually changing the value, I'm just changing the way that the value looks. And so now I'm going to distribute that 2 over both of these terms. That 2 must distribute over both of these terms. So my numerator here is going to be 2 times v naught v minus 2 v naught squared. And then this is all going to be over 2a now, right? I have common denominator here now, so I can write it as a single fraction. But then I also must have these 3 terms also in the numerator. So I'll have a plus v squared, final velocity squared, minus 2 times initial velocity times final velocity plus final velocity squared. And I know this looks gross, but we can simplify this now, because I have a 2 v naught v and I have a minus 2 v naught v. So 2 v naught v minus 2 v naught v is 0. So those cancel each other out. And then notice I also have a negative 2 v naught squared and a positive v naught squared. So we can combine those terms. Those are definitely like terms. And so when I do that, my left side is still just displacement. Displacement is going to be, what do I have left over? I have a v squared. And then when I combine negative 2 v naught squared and v naught squared, I have minus v naught squared, all divided by the denominator, which is 2a. And I'm almost there. I'm almost to kinematic equation number 3. But notice there's no fractions in kinematic equation number 3. I don't particularly care for fractions. So when I can get rid of them, I do. So to get rid of the fraction here, I multiply both sides by 2a. And so that cancels over here on the right side. And on the left side, I end up with 2a times delta x equals final velocity squared minus initial velocity squared. And then notice that kinematic equation number 3 is solved for the final velocity. So I want to get final velocity by itself. To do that, all I need to do is add initial velocity squared to both sides. And on the left side, I then have 2 times the acceleration times the displacement plus the initial velocity squared equals the final velocity squared. Now I can flip these. I can put the left side on the right and the right side on the left and the left side on the right. When I do that, I just get v squared equals, and I can rearrange the order in which I add these terms. So I'll have v naught squared plus 2a times the displacement delta x. That is essentially kinematic equation number 3, but I'm just going to expand it out and add the subscripts back in because, again, I know I'm dealing with the horizontal direction. So v squared I'm going to write as final velocity in the x direction squared equals, and this will be vx naught squared, initial velocity in the x direction squared, plus 2 times the acceleration, and then delta x I can always expand out to final minus initial position. So then I have final position minus initial position, and there is kinematic equation number 3. So why do we have 3 of them? Well, we have 3 of them because in certain problems, certain situations, there's certain variables that we don't have and that we're not asked to calculate. And so we use our given information and the quantity that we're asked to calculate, we use that list of variables in order to pick the proper kinematic equation. Notice that kinematic equation number 1 has nothing about positions or displacements. There's no x's, x naughts, delta x's, none of that. Kinematic equation number 2 doesn't have final velocity. There's no final velocities in there. Kinematic equation number 3 doesn't have time. When we made this time substitution, we eliminated the parameter time. And so if we have a problem that, say, doesn't ask for positions or displacements and doesn't give us any, we're probably going to be using kinematic equation number 1. If we have a problem where we're not given the final velocity and we're not asked to find the final velocity, we're probably going to use number 2 because it doesn't have final velocity in it. If we have a problem where we're asked to calculate, say, where we're not asked to calculate time and we don't have any information about the time, then we would use kinematic equation number 3, again, because it has no time in it. There's no time in it. So that's the purpose for having the 3 different kinematic equations. So after this, we're going to do an example problem. I'm going to show you how we do an example problem and the best way to solve your kinematics problems, the algebraic versions of your kinematics problems. But realize that everything, these 3 equations and all the work that I did to derive all 3 of the equations came directly from the velocity versus time graph for an object traveling with uniformly accelerated motion. That's the take-home point. These equations only work for uniformly accelerated motion. If you have a changing acceleration, you can't use these equations, and you have to use concepts that you'll learn in Physics C when you take that next year. And if you have, notice that if you have constant velocity motion, these equations are still valid, but if motion is or velocity is constant velocity, if you have constant velocity, then the acceleration must be 0. If you're not accelerating, then you're traveling with constant velocity. So say kinematic equation number 1, the acceleration would be 0, and you see that the final velocity is just the initial velocity. Just so you know, the constant velocity equation, sometimes it's called, it's rewritten from our kinematic equation number 2, final position equals initial position plus initial velocity times time plus 1/2 the acceleration times the time squared. But if the acceleration is 0, this entire term is 0. And then I have final position equals initial position plus initial velocity times time. So some students like to just memorize that because anytime you're dealing with constant velocity motion, this is pretty much the only equation you'll ever need. Okay. Other than that, that's your introduction to the 3 kinematic equations. They are the first 3 kinematic equations listed on your formula sheet, and I'll see you in the next one.